To understand gravitational waves, you must first abandon the comfortable intuition that space is empty. The classical picture inherited from Newton imagined space as a fixed, invisible stage on which matter performs its motions, a neutral backdrop that itself does nothing and changes nothing. Einstein demolished this picture in 1915 with his general theory of relativity, replacing it with something far stranger and more beautiful, a dynamic, flexible fabric called spacetime, in which space and time are unified into a single four-dimensional continuum that can bend, curve, stretch, and ripple in response to the presence of mass and energy. It is in this curved fabric that gravity lives. The Earth orbits the Sun not because an invisible force pulls it across empty space as Newton described, but because the Sun's mass curves the space-time around it, and the Earth follows the straightest possible path through this curved geometry, a path that traces out an orbit. This picture of gravity as geometry, as the curvature of space-time caused by mass and energy, has a dynamic consequence that Newton's theory entirely lacked. It predicts that when massive objects accelerate, they should disturb the curvature of spacetime in ways that propagate outward as waves. Just as accelerating electric charges produce electromagnetic waves, accelerating masses produce gravitational waves. These are not waves of any substance traveling through spacetime. They are waves of spacetime itself, oscillating distortions in the geometry of the four-dimensional fabric, spreading outward from their source at the speed of light. The physical character of gravitational waves is strange and counterintuitive. As a gravitational wave passes through a region of space, it alternately stretches and compresses distances in perpendicular directions. Imagine a ring of freely floating particles arranged in a circle in the plane perpendicular to the wave's direction of travel. As the wave passes, the ring is distorted into an ellipse stretched in one direction, then snaps back to a circle, then is stretched in the perpendicular direction, then returns to a circle again. This oscillating, stretching, and squeezing is the physical signature of a gravitational wave, and it is what gravitational wave detectors are built to measure. The technical name for the magnitude of this stretching is strain, defined as the fractional change in length. A strain of 1 part in 10 to the 21st means that a length of 1 meter has been stretched by 1 atometer, 1/1000th of a meter, less than 1,000th of the diameter of an atomic nucleus. The reason gravitational waves carry such fantastically small strains by the time they reach Earth is not because they start weak. At their source, in the final fraction of a second, of a black hole merger, gravitational waves carry energy at a rate that dwarfs everything else in the observable universe. But gravitational waves weaken with distance, their strain falling as 1 over the distance from the source, and the cosmic distances involved mean that by the time any wave reaches our planet, its amplitude has been diluted to nearly nothing. The first gravitational wave ever detected, from a black hole merger 1.3 billion light-years away, distorted LIGO's 4-kilometer arms by about 4,000ths the diameter of a proton. That this was detected at all is one of the most stunning achievements in the history of experimental science. Gravitational waves are fundamentally different from every other type of wave known to physics in several important respects. Electromagnetic waves, including light, radio waves, and gamma rays, are oscillations of electric and magnetic fields that propagate through spacetime. Sound waves are oscillations of pressure in a medium. Quantum mechanical matter waves describe the probability distribution of particles. All of these wave types propagate through spacetime, using it as a stage. Gravitational waves are distortions of spacetime itself. They do not travel through anything. They are themselves a distortion of the medium in which everything else exists. This makes them uniquely penetrating, because they are not interacting with matter as they travel, but simply reshaping the geometry through which matter moves. They pass through all forms of matter with virtually no attenuation. A gravitational wave generated at the center of a neutron star emerges from the other side unchanged, carrying information about the most extreme environments in the cosmos to any detector patient and precise enough to register their passage. The existence of gravitational waves follows mathematically from the field equations of general relativity, with a directness that left Einstein himself ambivalent about whether the prediction was genuine or merely a mathematical artifact. The linearized form of the field equations, valid for weak gravitational fields, reduces to wave equations whose solutions are transverse waves propagating at the speed of light. Einstein published this prediction in 1916, just 1 year after completing the general theory of relativity. But for much of his subsequent career, he doubted that gravitational waves were real physical phenomena with observable effects, famously co-authoring a paper in 1936 that argued they did not exist, only to discover an error in the calculation and quietly withdraw it. The physical reality of gravitational waves was established indirectly in 1974 and directly in 2015, nearly a century after the prediction was made, in one of the most remarkable confirmations in the history of scientific theory. The discovery of gravitational waves has opened what astronomers call a new window on the universe. Every previous branch of astronomy was based on detecting electromagnetic radiation of some wavelength, from radio waves to gamma rays, each carrying a different kind of information about cosmic sources. Gravitational waves carry a fundamentally different kind of information encoded in the geometry of spacetime rather than in the properties of electromagnetic fields. They reveal aspects of cosmic events, the strong field dynamics of merging compact objects, the ringing of a newly formed black hole as it settles into its final state, that are completely invisible to electromagnetic observation. Astronomy with gravitational waves is not merely an extension of existing electromagnetic astronomy. It is the beginning of an entirely new science, one that reads the universe in a language that required Einstein's revolutionary reimagining of space, time, and gravity to first make possible. When Albert Einstein published his general theory of relativity in November 1915, he completed one of the most audacious intellectual achievements in human history, a complete reformulation of the nature of gravity, space, and time that replaced Newton's action at a distance force with the curvature of a four-dimensional space-time fabric. Within months, Einstein had extracted from his field equations the prediction that accelerating masses should produce waves in this fabric, oscillating distortions propagating outward at the speed of light. He called them gravitational waves. And he published this prediction in 1916 in a paper presented to the Prussian Academy of Sciences. Then followed one of the strangest episodes in the relationship between theory and experiment in all of physics. A wait of 99 years before anyone could confirm that these waves actually exist. The wait was not for lack of trying, or for lack of conviction that the prediction was worth testing. It was a wait imposed by the extraordinary difficulty of the detection problem. Einstein's own back-of-the-envelope estimates of the amplitude of gravitational waves from any conceivable laboratory source were so small that he concluded detection would be forever beyond the reach of experiment. In this, unusually for Einstein, he was being insufficiently imaginative. He was thinking of the gravitational waves that a person or a machine could produce, where the masses are at most a few tons and the velocities far below the speed of light. He apparently did not seriously consider the waves that would be produced by masses of stellar dimensions moving at relativistic velocities, the black holes and neutron stars that are now the primary targets of gravitational wave astronomy. When the relevant sources are not laboratory apparatus but colliding black holes each 50 times the mass of the Sun, the gravitational waves, though still astonishingly faint by the time they reach Earth, are at least potentially detectable. With sufficiently clever technology, the theoretical development that preceded detection was long and sometimes confused. Einstein's own relationship with gravitational waves was notably complicated. In 1936, he and his assistant Nathan Rosen submitted a paper to Physical Review arguing that gravitational waves did not actually exist, that the wave solutions of the field equations were artifacts of coordinate choice rather than physical phenomena. The reviewer, who has since been identified as Howard Percy Robertson, found a critical error in the calculation. Einstein was furious at the review process, refusing to submit to Physical Review again, but the error was real. The paper was corrected and published elsewhere with the opposite conclusion. Gravitational waves did exist and did carry energy. This episode illustrates the difficulty of working with the nonlinear mathematics of general relativity even for its creator. The question of whether gravitational waves carry real physical energy was settled definitively only in 1957 at a conference in Chapel Hill, North Carolina, where Richard Feynman presented what became known as the sticky bead argument. Feynman imagined a gravitational wave passing through a rod with two beads threaded on it, free to slide. The wave would alternately move the beads toward and away from each other, and friction between the beads and the rod would generate heat, demonstrating that energy was being deposited by the wave. If gravitational waves could heat a rod, they were real physical phenomena carrying genuine energy. This argument, which convinced most of the conference, also helped motivate the first serious experimental attempts to detect gravitational waves. The first detector was built by Joseph Weber at the University of Maryland in the early 1960s. Weber's device, an aluminum cylinder roughly 2 meters long and 1 meter in diameter, was designed to resonate at the frequency of gravitational waves from anticipated astrophysical sources. When a gravitational wave of the right frequency passed through the cylinder, the alternating stretching and squeezing of spacetime would cause the cylinder to vibrate, and these vibrations could be detected by piezoelectric sensors attached to its surface. Weber operated 2 such cylinders, one in Maryland and one in Illinois, and in 1969 he announced that he had detected coincident signals suggesting genuine gravitational wave events. The scientific community reacted with cautious excitement, but subsequent attempts by other groups to replicate Weber's results failed. The sensitivity of his detectors was eventually shown to be many orders of magnitude too low to detect the gravitational waves from any realistic astrophysical source. Whether Weber genuinely detected something remains debated, but the consensus view is that his results were not gravitational waves. The indirect evidence that gravitational waves existed and behaved exactly as general relativity predicted came in 1974 from an unexpected source. Russell Hulse and Joseph Taylor, working at the Arecibo Radio Telescope in Puerto Rico, discovered a pulsar in a binary system, a rapidly rotating neutron star orbiting an unseen companion that turned out itself to be a neutron star. This system, designated PSR B1913+16, provided a natural laboratory for testing general relativity in the strong field regime. One of the most striking predictions of general relativity is that a binary system of compact objects should lose energy through gravitational wave emission, causing the orbit to slowly decay as the 2 objects spiral closer together. Taylor and his colleagues measured the orbital period of the Hulse-Taylor binary with extraordinary precision and tracked its change over years. The orbital period was decreasing at exactly the rate predicted by general relativity for energy, lost through gravitational wave emission, to within a fraction of a percent. This was not a direct detection of gravitational waves, but it was compelling evidence that they existed and carried away energy at the predicted rate. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. The direct detection that confirmed Einstein's century-old prediction came on September 14, 2015, at 5:51 in the morning Eastern Time in the United States, when LIGO registered the signal from 2 merging black holes. The signal lasted 0.2 seconds, sweeping upward in frequency from 35 to 150 Hz in a characteristic chirp pattern, and its amplitude matched the predictions of general relativity for a merger at 1.3 billion light-years with initial black hole. Masses of 36 and 29 solar masses, producing a final black hole of 62 solar masses. The 3 missing solar masses had been radiated as gravitational waves in an instant, releasing more energy than all the stars in the observable universe combined emit in that same fraction of a second. The century wait was over. Einstein was right. Every science student learns early that light is a wave. They learn that it consists of oscillating electric and magnetic fields perpendicular to each other and to the direction of propagation, rippling outward from a source at the universal speed limit of approximately 300,000 kilometers per second. They learn that this electromagnetic wave can travel through a vacuum because it does not need a medium to propagate. Unlike sound, which requires air or some other material to compress and rarefy, light carries its own field oscillations with it across empty space. This is already conceptually demanding, and it represented a major advance in physics when Maxwell unified electricity, magnetism, and light in the 1860s. But electromagnetic waves, despite their ethereal ability to travel through vacuum, are still fundamentally waves traveling through spacetime. They use the 4-dimensional fabric of Einstein's universe as the medium in which they exist and propagate. Gravitational waves are categorically different. They are not oscillations propagating through spacetime. They are oscillations of spacetime itself. This is not a subtle semantic distinction. It reflects a fundamental difference in the physical nature of the phenomenon. When a gravitational wave passes through a region of space, it does not deposit energy into any pre-existing field. It does not excite any medium. It changes the geometry. The actual distances between points in space oscillate. The actual rate at which time flows oscillates. The metric of spacetime, the mathematical object that defines how distances and time intervals are measured throughout the universe, undulates as the wave passes. Everything in the affected region is subject to this geometric oscillation, and there is no position, no reference frame, no material that is immune to it. This geometric nature of gravitational waves has a profound consequence for how they interact with matter. Electromagnetic waves interact with matter through the electromagnetic force. They push and pull on charged particles, exciting electrons to higher energy levels, inducing currents in conducting materials, heating absorbing surfaces through photon-phonon interactions. Materials that are transparent to visible light are opaque to ultraviolet. Materials transparent to X-rays absorb gamma rays. Every material has a characteristic interaction profile with electromagnetic radiation because every material has a characteristic electromagnetic structure that determines how strongly it couples to passing electromagnetic waves. Gravitational waves have no such coupling. The interaction of a gravitational wave with matter is purely geometric. The wave stretches and squeezes the distances between freely falling test masses, and this effect is the same for all types of matter because it is not a force acting on matter, but a change in the geometry through which matter moves. The consequence is that gravitational waves pass through matter with essentially no attenuation at all. A gravitational wave generated at the center of a stellar collapse, surrounded by a shell of dense neutron star matter dozens of kilometers thick, passes through this matter as if it were not there, carrying information about the collapse dynamics directly to any detector in the universe. A gravitational wave from a merger 13 billion light-years away, having traveled through billions of light-years of gas, dust, dark matter, and normal matter, arrives at Earth with the same amplitude it would have had if that space had been perfectly empty, reduced only by the geometric dilution that comes from spreading over an ever larger sphere. This penetrating power makes gravitational waves, in principle, messengers from events and environments that are completely invisible to electromagnetic astronomy. The most extreme example of this penetrating advantage is the Big Bang itself. Electromagnetic astronomy is limited in how far back in time it can observe because the early universe was opaque to photons. For the first 380,000 years after the Big Bang, the universe was a hot, dense plasma in which photons were constantly scattered by free electrons, unable to travel freely. The cosmic microwave background, the oldest electromagnetic signal we can detect, comes from the moment 380,000 years after the Big Bang when the universe cooled enough for electrons and protons to combine into neutral hydrogen, making the universe transparent to photons for the first time. Everything before that moment is invisible to any electromagnetic telescope, no matter how powerful. Gravitational waves from the first fractions of a second of the universe, if they exist and can be detected, would carry information about the Big Bang era that is entirely inaccessible by any other observational means. The polarization of gravitational waves is another property that distinguishes them from electromagnetic waves in a fundamental way that reflects their origin in spacetime geometry. Electromagnetic waves are transverse waves with two polarization states, which correspond to the two orientations of the oscillating electric field perpendicular to the direction of propagation. Gravitational waves, as predicted by general relativity, also have two polarization states, conventionally called plus polarization and cross polarization. In plus polarization, the wave stretches space along one axis while compressing it along the perpendicular axis. In cross polarization, the same pattern occurs but rotated 45 degrees. The two polarization nature of gravitational waves is a direct consequence of the tensor character of the gravitational field in general relativity, and measuring the polarization of detected waves provides a test of the theory. Alternative theories of gravity predict different numbers of polarization states, so measuring the polarization content of gravitational waves can test whether general relativity is the correct description of gravity in the strong field dynamical regime probed by merging compact objects. The speed of gravitational waves, identical to the speed of light in vacuum, is a fundamental prediction of general relativity that was tested with extraordinary precision in 2017 when the neutron star merger GW170817 was detected simultaneously in gravitational waves and in electromagnetic radiation. The gravitational wave signal arrived 1.7 seconds before the gamma ray burst from the same event. Given the 130 million light-year distance to the source, this time difference corresponds to a speed difference between gravitational waves and light of less than 1 part in 1,000 trillion. No alternative theory of gravity that predicted significantly different speeds for gravitational and electromagnetic waves survived this observation. The wave that Einstein predicted in 1916, emerging from the geometry of spacetime rather than from any field propagating through it, travels at exactly the speed limit of the universe, confirming that gravity and electromagnetism share the same fundamental causal structure of relativistic spacetime. For most of the history of physics, the speed of gravity was a theoretical question with no experimental answer. Newton's theory of gravity did not even address the question in a meaningful way. In Newtonian mechanics, gravitational influences propagate instantaneously across any distance. If the sun were to suddenly disappear, Newton's theory predicted that the Earth would immediately feel the absence of gravitational pull and fly off in a straight line, without any delay for the news to travel across the 150 million kilometers separating the two bodies. This instantaneous action at a distance was philosophically troubling to many physicists, including Newton himself, who wrote that the idea of action at a distance without a mediating mechanism seemed absurd, but he declined to speculate about the underlying cause. Einstein's general theory of relativity resolved this philosophical discomfort decisively. In general relativity, gravitational influences propagate at the speed of light, the universal maximum speed permitted by the structure of spacetime. Changes in the gravitational field propagate outward from their source as gravitational waves, and these waves travel at exactly c, the speed of light in vacuum, approximately 299,192 kilometers per second. This is not a coincidence or an approximation. It is a deep theoretical prediction that reflects the fact that both electromagnetic waves and gravitational waves are disturbances of the same four-dimensional spacetime fabric, and both are constrained by the same causal speed limit that special relativity imposes on all forms of information transfer. The theoretical prediction that gravity travels at the speed of light was difficult to test directly because the detectable effects of gravitational wave propagation speed require either enormous distances between source and detector or extraordinary measurement precision. The most prominent attempt before LIGO involved the motion of Jupiter. In 2002, Sergei Kopeikin and colleagues attempted to measure the speed of gravity using a technique based on the bending of light from a distant radio source as it passed close to Jupiter, arguing that the precise position of the light deflection depended on the speed of gravity. This experiment yielded a result consistent with the speed of light, but the interpretation was controversial, with critics arguing that the measurement was actually sensitive to the light deflection from Jupiter's static gravitational field rather than to the propagation speed of gravitational influences. The debate illustrates the theoretical subtlety of defining and measuring the speed of gravity in a consistent theoretical framework. The definitive measurement came from the cosmos itself, in the form of the neutron star merger event designated GW170817, detected on August 17, 2017. At 12:41:04 Universal Time, the LIGO and Virgo detectors registered the gravitational wave signal from two neutron stars spiraling together and merging approximately 130 million light-years away in the galaxy NGC 49923. The gravitational wave signal swept upward in frequency over approximately 100 seconds as the neutron stars accelerated toward their final merger, a pattern entirely consistent with the predictions of general relativity. Then, 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope and the Integral Satellite detected a short gamma ray burst from the same direction in the sky. The same merger that had produced the gravitational wave signal had also produced a burst of gamma radiation, and the two signals, having traveled 130 million light-years, arrived within less than 2 seconds of each other. The constraint this places on the relative speed of gravitational waves and light is extraordinary. If gravitational waves traveled at a speed different from light by even a tiny fraction, The difference would accumulate over 130 million light-years to a measurable time delay. The 1.7-second gap between arrival times corresponds to a fractional speed difference of at most about 3 parts in 10 to the 15th, or 0.1%. Gravitational waves and electromagnetic waves travel at the same speed to this extraordinary precision. This result instantly ruled out a large class of alternative theories of gravity that predicted different propagation speeds for gravitational and electromagnetic waves, including many theories proposed as explanations for dark energy that predicted gravitational waves would travel faster than light. The theoretical significance of the speed constraint extends beyond confirming general relativity. The equality of the speed of gravitational waves and light is deeply connected to fundamental properties of spacetime and of the particles that carry these interactions. Light is carried by photons, which are massless particles that travel at exactly c. Gravitational waves, in the quantum mechanical description of gravity that physicists are working toward, would be carried by gravitons, hypothetical massless, spin 2 particles. A graviton with non-zero mass, however small, would cause gravitational waves to travel slower than light, with lower frequency waves being affected more than higher frequency ones. The GW170817 measurement placed an upper limit on the graviton mass of about 10 to the power of minus 22 electron volts, an extraordinarily stringent constraint that is among the strongest limits on graviton mass from any observation. The 1.7-second gap between gravitational and electromagnetic arrival from GW170817, rather than being interpreted as a violation of speed equality, is understood as a physical delay between the moment of merger and the moment of gamma-ray burst production. The merger itself, which produced the gravitational waves, occurred at the moment of coalescence. The gamma-ray burst requires the formation of a jet of relativistic plasma that must punch its way through the debris of the merger before producing detectable gamma rays, and this process takes a finite time after the merger. The 1.7-second delay is thus a delay between the gravitational wave production and the gamma-ray production, not between their subsequent propagation, consistent with astrophysical models of short gamma-ray burst formation. The remarkable concordance of this picture with theoretical expectations for neutron star mergers was one of many aspects of GW170817 that made it the most scientifically rich gravitational wave event yet detected. Numbers in physics sometimes surpass human intuition so completely that they cease to function as genuine quantities and become merely abstract labels for inconceivable magnitudes. The strain of the first detected gravitational wave is such a number. The strain, technically defined as the fractional change in length produced by the wave, was approximately 10 to the power of minus 21 for the GW150914 event. Written out, this is 0.0101101, a decimal point followed by 20 zeros and then a 1. Applied to LIGO's 4-kilometer arms, this strain represents a change in length of roughly 4 times 10 to the power of minus 18 meters, 4 attometers, about 4/1000ths of the diameter of a proton. The proton itself is roughly 10 to the power of minus 15 meters across, so the displacement LIGO measured was smaller than a proton by a factor of about 250. That any instrument built by human hands could detect a distance change this small is, without hyperbole, one of the most extraordinary engineering and scientific achievements in the history of civilization. To build intuition for this scale, consider a sequence of comparisons that descend through the orders of magnitude between human perception and the gravitational wave displacement. A human hair is roughly 70 micrometers in diameter, about 70,000 nanometers. A typical bacterium is about 1 micrometer long. A DNA double helix is about 2 nanometers in diameter. A hydrogen atom is about 0.1 nanometers. An atomic nucleus, where protons and neutrons are packed together by the strong nuclear force, is about 1 femtometer, 10 to the power of minus 15 meters, in diameter. And the displacement that LIGO measured is 1,000 times smaller than this already unimaginably tiny nuclear scale. LIGO did not measure a displacement of a nucleus. It measured a displacement 1,000th the size of a nucleus. The challenge of measuring such a displacement is not merely technological but conceptual. How does one measure a distance change smaller than any material object in the universe? The answer LIGO uses is interferometry, the technique of comparing the lengths of two paths by measuring the interference between light waves that have traveled along them. A laser beam is split into two perpendicular beams by a beam splitter, and each beam travels down one of LIGO's 4-kilometer arms to a mirror at the end, where it is reflected back. When the two beams are recombined, they interfere. If the two arms are exactly equal in length, the beams interfere destructively, and no light reaches the detector. If a gravitational wave has stretched one arm relative to the other, the path-length difference causes the interference to become partially constructive, and a small amount of light reaches the detector. The brightness of this light signal is precisely proportional to the arm-length difference, which is proportional to the strain of the passing gravitational wave. The principle is elegant, but the practical implementation requires overcoming an almost endless list of noise sources that would otherwise swamp the tiny gravitational wave signal. Thermal noise causes the mirror surfaces to jitter as individual atoms vibrate at room temperature. Seismic noise from traffic, ocean waves, and distant earthquakes causes the entire mirror system to vibrate on a large scale. Quantum mechanical shot noise in the laser light itself imposes a fundamental limit on the precision of length measurement due to the Heisenberg uncertainty principle. Each of these noise sources, if not mitigated, would produce mirror displacements far larger than the gravitational wave signal being sought. The mitigation of seismic noise is achieved through a suspension system of extraordinary sophistication. Each of LIGO's main mirrors, which weigh 40 kilograms and are polished to atomic flatness, is suspended from a 4-stage pendulum system, each stage providing vibration isolation from the stage above. The lowest resonant frequency of the lowest pendulum stage is about 1 Hz, below the frequency band of interest for gravitational wave detection, so that seismic noise at higher frequencies is attenuated by many orders of magnitude before reaching the mirrors. Additional active noise cancellation, using seismometers that measure ground motion and actuators that apply equal and opposite forces to the suspension, further reduces the seismic contribution to mirror motion. The final result is that the mirror's residual seismic motion in the detection band of a few tens to a few hundreds of hertz is reduced to a level comparable to the signal sought. Thermal noise is addressed through the choice of mirror material and temperature. LIGO's mirrors are made from fused silica, a form of glass with an exceptionally low mechanical loss, meaning that thermal energy couples weakly to the mirror's internal vibration modes. The suspension fibers are also made from fused silica for the same reason. These choices minimize the thermal noise floor, though they do not eliminate it, and future detectors may use cryogenically cooled sapphire mirrors, as the Japanese Kagra detector does, to further reduce thermal noise by lowering the temperature at which the mirrors vibrate. The quantum noise limit, imposed by the particle nature of light, is addressed through the use of squeezed light, a quantum optical technique that redistributes the quantum uncertainty of the light field to reduce the uncertainty in the phase measurement relevant for interferometry at the cost of increased uncertainty in the amplitude. LIGO has incorporated squeezed light injection since 2019, pushing the measurement sensitivity closer to the standard quantum limit. Future detectors may use even more sophisticated quantum optical techniques to further reduce this fundamental noise floor. The combination of all these noise mitigation strategies, along with the sheer physical size of LIGO's 4-kilometer arms that amplifies the gravitational wave signal relative to most non-gravitational noise sources, produces a detector of literally unprecedented sensitivity. The measurement of a strain of 10 to the power of -21 is not a precision that can be achieved with a ruler, a micrometer, or any conventional distance measuring tool. It is a precision achieved by exploiting the wave nature of light, the quantum properties of photon statistics, the mechanics of multi-stage pendulum isolation, and the subtleties of laser frequency stabilization, all combined in a system whose entire purpose is to detect the passage of a wave of spacetime geometry that Einstein predicted in 1916, and whose amplitude he thought would be forever beyond human detection. Not everything that moves produces detectable gravitational waves. The strength of the gravitational wave signal from an accelerating mass depends on how asymmetric the acceleration is, how much mass is involved, how fast the motion is relative to the speed of light, and how close the source is. A spinning sphere produces no gravitational waves at all because its mass distribution is perfectly symmetric. There is nothing to distinguish one moment from the next in terms of the quadrupole structure of its mass distribution. A spinning dumbbell, on the other hand, produces quadrupole gravitational radiation as its mass distribution changes periodically with each rotation. Scaling this up to cosmic dimensions, the objects that produce gravitational waves strong enough to be detectable from Earth are those in which enormous masses, moving at substantial fractions of the speed of light, undergo highly asymmetric accelerations. In practice, three categories of astrophysical events dominate the landscape of gravitational wave sources: merging black holes, merging or colliding neutron stars, and asymmetric stellar collapse in supernovae. Black hole mergers are, by a wide margin, the most productive gravitational wave factories known. When two black holes are in orbit around each other, they lose orbital energy through gravitational wave emission and spiral closer together. As they spiral inward, their orbital frequency increases, and the frequency of the gravitational waves they emit increases correspondingly, producing a characteristic chirp pattern that rises in frequency and amplitude until the moment of merger. In the final fraction of a second of a merger between two black holes, each tens of solar masses in size, the power radiated as gravitational waves exceeds the electromagnetic luminosity of all stars in the observable universe combined. This extraordinary power output is possible because the merging black holes are objects of near maximum gravitational compactness, moving at velocities approaching the speed of light in configurations so asymmetric and so dynamically extreme that the quadrupole gravitational radiation formula predicts enormous wave amplitudes. The masses of the black holes LIGO has observed merging have ranged from a few solar masses to over 100 solar masses, revealing a population of stellar mass black holes that was entirely unknown before gravitational wave observations. Prior to LIGO, stellar mass black holes were known only from X-ray binary systems, where a black hole accretes material from a companion star and emits powerful X-rays in the process. The black holes known from X-ray binaries rarely exceeded about 20 solar masses. LIGO's detections have included black holes of 30, 40, 50, and even over 80 solar masses in the pre-merger objects, revealing a population of massive black holes whose formation and evolution is not yet fully understood. Some of these mergers may involve black holes that formed not from single massive stars but from previous mergers of smaller black holes, building up in mass through a hierarchical sequence of mergers in dense stellar environments. Neutron star. Mergers are the second major category of gravitational wave source, and in some respects the most scientifically rich. Neutron stars, the remnants of supernova explosions of intermediate mass stars, are objects of extraordinary density. A neutron star of 1.4 solar masses is compressed into a sphere only about 12 kilometers in radius, making it so dense that a teaspoon of neutron star matter would weigh about 1 billion tons on Earth. When two neutron stars orbit each other in a binary system, losing orbital energy through gravitational wave emission as the Hulse-Taylor system elegantly demonstrated, they spiral together over timescales of hundreds of millions of years, eventually merging in an event of enormous violence. The merger produces a burst of gravitational waves whose character depends on whether the merged object collapses immediately to a black hole or first forms a hypermassive neutron star that survives for some time before collapsing, encoding information about the equation of state of ultra-dense nuclear matter in the gravitational wave signal. Beyond their gravitational wave emission, neutron star mergers are the sites of some of the most energetically extreme and nucleosynthetically important processes in the universe. The merger ejects a portion of the highly neutron-rich material of the neutron stars into space, creating conditions of extreme neutron flux in which rapid neutron capture, the R process, can occur. The R process, which requires a neutron-to-seed nucleus ratio far higher than can be achieved in stellar interiors or even in most supernova environments, is responsible for the creation of the heaviest elements in the periodic table: gold, platinum, lead, uranium, and dozens of other heavy elements that could not be produced by the slower neutron capture processes that occur in the interiors of evolved stars. Before GW170817, the site of the R process was debated, with supernova explosions and neutron star mergers being the primary candidates. The detection of GW170817 and the optical follow-up observations that revealed a kilonova, a luminous transient, powered by the radioactive decay of freshly synthesized heavy elements, confirmed that neutron star mergers are a primary site of heavy element synthesis. The gold in your jewelry was almost certainly forged in a neutron star merger billions of years ago. Supernovae, the explosive deaths of massive stars, are the third potential category of gravitational wave sources, though none have been detected in gravitational waves yet. The gravitational wave emission from a core collapse supernova depends on how asymmetric the collapse is. A perfectly spherical collapse would produce no gravitational waves, while a highly asymmetric collapse in which the core bounces or fragments produces a burst of gravitational waves whose character encodes information about the collapse dynamics deep in the stellar interior. Even LIGO in its current configuration could detect a core collapse supernova in our galaxy or the nearest galaxies. The challenge is that such events are rare, perhaps one per century per galaxy, and predicting when and where to look for them is not currently possible. When the next galactic supernova occurs, gravitational wave detectors will provide information about the core collapse dynamics that is completely inaccessible to electromagnetic observations, which see only the outer envelope of the exploding star long after the bounce has occurred. Supernovae, the explosive deaths of massive stars, are the third potential category of gravitational wave sources, though none have been detected in gravitational waves yet. The gravitational wave emission from a core collapse supernova depends on how asymmetric the collapse is. A perfectly spherical collapse would produce no gravitational waves, while a highly asymmetric collapse in which the core bounces or fragments produces a burst of gravitational waves whose character encodes information about the collapse dynamics deep in the stellar interior. Even LIGO in its current configuration could detect a core collapse supernova in our galaxy or the nearest galaxies. The challenge is that such events are rare, perhaps one per century per galaxy, and predicting when and where to look for them is not currently possible. When the next galactic supernova occurs, gravitational wave detectors will provide information about the core collapse dynamics that is completely inaccessible to electromagnetic observations, which see only the outer envelope of the exploding star long after the bounce has occurred. At 5:51 in the morning of September 14, 2015, Eastern Daylight Time in the United States, an automated alert system at the Laser Interferometer Gravitational Wave Observatory registered an anomalous signal in both of its detectors. The two detectors, one in Hanford, Washington, and one in Livingston, Louisiana, had recorded nearly identical disturbances in the differential length of their 4-kilometer arms, with the Livingston detector registering the signal 7 milliseconds before the Hanford detector, consistent with a signal traveling across the 3,000 kilometers separating the sites at the speed of light. The signal was a sweeping chirp, a rapid increase in the frequency and amplitude of the arm-length oscillation, rising from about 35 to 150 Hz over 0.2 seconds, followed by an abrupt cessation. To the physicists who analyzed it, the shape was unmistakable. It was a gravitational wave from a binary black hole merger. It was what they had been looking for, preparing for, and working toward for decades. The LIGO collaboration had been preparing for this moment since the early 1990s. The instrument that made the detection was actually LIGO's second major configuration, called Advanced LIGO, which had just reached design sensitivity after years of upgrades that improved the strain sensitivity by roughly an order of magnitude over the original LIGO instrument. The new configuration had been collecting data for only 4 days when GW170914 arrived, making the detection not just scientifically historic but historically ironic. The first signal came almost immediately, before the observers had even had time to worry that it might be years before something appeared. The analysis of the signal required months of careful work by hundreds of physicists to confirm its authenticity and extract the physical parameters of the source. The primary tool was matched filtering against a bank of theoretical waveform templates generated by numerical relativity simulations of merging black holes with various masses and spins. The best matching template, which fit the observed signal with extraordinary precision, corresponded to a merger between two black holes with masses of approximately 36 and 29 solar masses at a distance of about 1.3 billion light-years, producing a final black hole of approximately 62 solar masses. The difference between the total initial mass of 65 solar masses and the final mass of 62 solar masses represents 3 solar masses of energy radiated as gravitational waves during the merger, an amount of energy equal to about 6 times 10 to the power of 47 joules, released in a fraction of a second. To put this energy release in perspective, the Sun, in its entire 10 billion year lifetime, will radiate approximately 10 to the power of 44 joules of electromagnetic energy. The G-912 merger radiated in gravitational waves in a fifth of a second, about 1,000 times the total electromagnetic energy output of the Sun over its entire lifetime. The power output during the final moments of the merger, roughly 3 times 10 to the power of 49 watts, exceeded the combined electromagnetic luminosity of all the stars in the observable universe by a factor of about 50. The universe had announced itself to its new observers with considerable enthusiasm. The confirmation process for GW150914 was exhaustive. The LIGO collaboration performed hundreds of tests for instrumental artifacts, looking for any way in which the signal could have been produced by something other than a genuine gravitational wave. They examined the data for correlations with known noise sources, power grid interference, electromagnetic transients, seismic events, radio frequency interference, acoustic vibrations. They checked whether the signal was present in channels that monitor the detector's environment, but not the gravitational wave channel. They analyzed the signal's consistency with the expected behavior of a gravitational wave, its propagation speed between the two detectors, its polarization properties, and its agreement with the specific waveform predicted by general relativity. For the best fit source parameters, every test was passed. The probability that the observed signal was a noise fluctuation rather than a real gravitational wave was calculated as less than 1 in 3.5 million, corresponding to a statistical significance of 5.1 sigma by the conventional standards of particle physics. The physical information encoded in the GB914 signal confirmed general relativity in the most extreme dynamical regime it had ever been tested in. The in-spiral phase, in which the two black holes spiral together before merger, matched the post-Newtonian approximation of general relativity over several dozen orbital cycles. The merger phase, in which the two black holes coalesced in a fraction of an orbital period, was described by numerical relativity. The ring-down phase, in which the newly formed 62 solar mass black hole oscillated and radiated gravitational waves as it settled into its final Kerr configuration, matched the quasi-normal mode frequencies predicted by general relativity for a spinning black hole of the inferred mass and spin. The agreement between observation and theory across all 3 phases was a triumph of both observational and theoretical physics. The announcement of GW914 on February 11, 2016 was accompanied by press conferences held simultaneously at the National Science Foundation headquarters in Washington and at research institutions across the world. The announcement attracted extraordinary attention from both the scientific community and the general public, partly because of the intrinsic importance of the result and partly because of the skillful communication by LIGO scientists of what the detection meant. The comparison of the signal to a chirp and the playing of the audio representation of the gravitational wave waveform, in which the frequency sweeps up through the human audible range before disappearing in the merger, made the abstract concept of space-time distortion viscerally real to audiences worldwide. Humanity had heard, for the first time, the sound of 2 black holes colliding more than 1 billion years ago. Astronomy is fundamentally the science of reading messages that have traveled to us from the cosmos, and for most of human history, those messages arrived exclusively in the form of visible light. The development of radio astronomy in the 1930s and 1940s opened the first new cosmic window, revealing sources invisible to optical telescopes. Successive decades brought X-ray astronomy, gamma-ray astronomy, infrared astronomy, and ultraviolet astronomy, each exploiting a different part of the electromagnetic spectrum to see phenomena that were invisible at other wavelengths. Neutrino astronomy, which detected a handful of neutrinos from the supernova SN 1987A in 1987, added a new kind of messenger beyond the electromagnetic spectrum. But all of these approaches share a fundamental limitation. They can only see events and objects from which some form of electromagnetic radiation, or neutrinos, actually escapes to reach our detectors. Gravitational wave astronomy operates on a different principle entirely and therefore has access to information that is categorically invisible to any electromagnetic approach. The most dramatic example of information hidden from electromagnetic astronomy is the interior of a black hole merger. The two black holes that merged in GW15500914 were, by definition, objects from which no light can escape. The event horizon of a black hole is the surface within which the escape velocity exceeds the speed of light, making electromagnetic radiation permanently trapped. The dynamics of two event horizons merging, stretching, oscillating, and settling into the event horizon of the merged black hole are entirely invisible to any telescope. No light or other electromagnetic radiation escapes from inside the event horizons or from the merger itself. The gravitational wave signal that LIGO detected was generated by the dynamics of this merger and propagated freely through the universe, passing through all intervening matter without interaction until it reached Earth. It is the only messenger from this event that the laws of physics permit to escape. A second category of information hidden from electromagnetic astronomy comes from the dense interiors of stellar collapse. When a massive star exhausts its nuclear fuel and the iron core at its center collapses to form a neutron star or black hole in a fraction of a second, the electromagnetic signature of this event, the supernova explosion, comes from the outer layers of the star being ejected by the shock wave generated at the core. The core itself, where the most dramatic gravitational dynamics occur, is buried under thousands of kilometers of dense stellar material that is opaque to electromagnetic radiation. Even the neutrinos produced in the core collapse, though they escape from the core and in principle carry information about the collapse dynamics, interact with matter enough that they are affected by the envelope through which they pass, and must be interpreted with models of the stellar structure. Gravitational waves from core collapse propagate from the innermost dynamics to the detector without any absorption or scattering, carrying pristine information about the bounce, the convective motions, and the subsequent neutron star oscillations that occur in the inaccessible interior. The universe's distant past represents a third domain of information hidden from electromagnetic astronomy. The cosmic microwave background, the oldest electromagnetic signal in the universe, comes from 380,000 years after the Big Bang. Everything before that time is hidden behind a wall of opacity. The universe was so hot and dense that photons were continuously scattered by free electrons, preventing them from traveling freely. The universe was electromagnetically opaque. Gravitational waves from events in the early universe, including the inflationary epoch in the first 10 to the power of -32 seconds, the electroweak phase transition at about 10 picoseconds after the Big Bang, and any other strongly first-order phase transitions or topological defect formation, would propagate freely through the opaque plasma because they interact with matter so weakly. Detecting these primordial gravitational waves would provide information about the universe's earliest moments that is completely inaccessible by any other means. The cosmic gravitational wave background, a stochastic background of gravitational waves from all unresolved sources throughout the history of the universe, carries an integrated record of every gravitational wave event that has occurred since the universe became transparent to gravitational radiation, which is essentially from the beginning. The amplitude and spectral shape of this background encodes information about the rates and mass distributions of black hole and neutron star mergers throughout cosmic history, about the cosmological expansion history, and potentially about early universe processes. Detecting and characterizing this background is one of the major goals of current and future gravitational wave observatories. The complementarity between gravitational wave and electromagnetic observations of the same event was demonstrated magnificently by the neutron star merger GW170817. The gravitational wave observation alone revealed the masses of the two neutron stars, their distance from Earth, the orientation of their orbital plane relative to our line of sight, and the total energy radiated in gravitational waves. The electromagnetic observations added an entirely different dimension. The gamma-ray burst revealed the existence and delay time of the relativistic jet. The kilonova optical transient revealed the production of heavy elements through the R process. The X-ray and radio afterglows traced the jet's interaction with the surrounding medium, and the host galaxy identification provided an independent distance measurement. Neither the gravitational wave observation nor the electromagnetic observations alone could have provided the complete physical picture that emerged from combining both. The concept of multi-messenger astronomy, in which gravitational waves are one of the messengers alongside electromagnetic radiation and neutrinos, represents the maturation of a new and more complete approach to understanding the universe. Each type of messenger carries different information about the source, subject, to different selection effects and observational biases, and is sensitive to different physical processes. Combining multiple messengers from the same event allows the physical picture to be constrained in ways that no single messenger could achieve. For events like neutron star mergers, where the physics involves nuclear matter at extreme densities, strong magnetic fields, relativistic jets, and explosive nucleosynthesis, this multi-messenger approach is not merely convenient but essential for understanding what is happening. Gravitational wave astronomy is not a replacement for electromagnetic astronomy. It is the newest and perhaps most fundamental addition to the full toolkit of cosmic observation. Somewhere in the universe, approximately 1.3 billion years ago, when the most complex form of life on Earth was a microbial mat of cyanobacteria, and the Cambrian explosion of animal life still lay 500 million years in the future, two black holes completed a journey that had begun hundreds of millions of years earlier. They had been orbiting each other, each roughly 30 times the mass of the Sun, spiraling gradually inward as their orbital energy drained away in the form of gravitational waves too weak for any civilization, had one existed, to detect. For hundreds of millions of years, this inspiral was so slow as to be imperceptible on human timescales. Two monstrous objects circling each other across a distance of hundreds of kilometers, each circuit taking fractions of a second, each slightly closer than the one before. Then, in the final moments, the inspiral accelerated. The orbital frequency increased, the gravitational wave emission grew, and in the final 0.2 seconds, the two black holes merged into one in a cataclysm of spacetime distortion that released more energy than the entire observable universe emits electromagnetically in that same time. The spacetime wave from this event reached Earth on September 14, 2015, and a machine in Washington State and another in Louisiana each felt it in turn, 7 milliseconds apart. Humanity's first direct detection of a gravitational wave had arrived. The event designated GW1500914 for the date of its detection, September 14, 2015, was in every way a suitable herald for the new science it inaugurated. Its source was among the most violent events the universe produces. Its detection required the most precise measurement ever made. Its analysis confirmed the most comprehensive and mathematically sophisticated theory in the history of physics. And its announcement to the world on February 11, 2016 generated a level of public and scientific excitement that had not attended a physics announcement since the Higgs boson discovery of 2012. The physical parameters of G1500914 were extracted from the gravitational wave signal through a process of Bayesian inference, comparing the observed waveform against a bank of millions of template waveforms generated by numerical relativity simulations of black hole mergers with varying masses, spins, and orbital configurations. The best fit solution placed the two initial black holes at masses of approximately 36 and 29 solar masses, with spin magnitudes that were relatively low, and the final merged black hole at approximately 62 solar masses, rotating at about 67% of the maximum spin allowed by general relativity. The remaining three solar masses were radiated as gravitational waves, approximately 5.4 times 10 to the power of 47 joules of energy, emitted in the final fraction of a second, a power output of approximately 3.6 times 10 to the power of 49 watts. The distance to the source, approximately 1.3 billion light-years, was estimated from the amplitude of the signal. Gravitational wave strain falls as 1 over distance from the source, and once the intrinsic amplitude is determined from the waveform shape, which encodes the masses and orbital dynamics, the observed strain gives the distance directly. This combination of the intrinsic properties determined from the waveform shape and the distance determined from the amplitude is called the gravitational wave standard siren method, and it is one of the most powerful features of gravitational wave astronomy. Unlike electromagnetic standard candles, gravitational wave sources are self-calibrating, requiring no external calibration through a cosmic distance ladder. The three phases of the GW15914 waveform in spiral, merger, and ring-down each tested a different regime of general relativity, and each matched theoretical predictions with impressive precision. The in-spiral phase, in which the two black holes orbit each other with gradually increasing frequency and amplitude, was described by post-Newtonian approximations to general relativity that are accurate when the orbital velocity is a significant, but not dominant fraction of the speed of light. The 16 orbital cycles visible in the LIGO data, spanning about a fifth of a second, tested these approximations in a regime where the orbital velocity reached about 60% of the speed of light. The merger phase, in which the two event horizons touched and coalesced, required full numerical relativity, the direct numerical integration of Einstein's field equations on a computational grid, and the agreement between the observed waveform and the numerical relativity predictions provided the most direct test yet of general relativity in the fully nonlinear strong field dynamical regime. The ring-down phase, lasting a few tens of milliseconds after the merger, was the signal of the newly formed black hole settling into its final state. A newly formed black hole is not immediately in the Kerr geometry, the rotating black hole solution of Einstein's equations that describes a stationary black hole completely in terms of its mass and spin. Instead, it is initially distorted, with bumps and asymmetries inherited from the merger, and these distortions oscillate and decay as the black hole radiates gravitational waves at its characteristic quasi-normal mode frequencies. These frequencies are determined entirely by the black hole's mass and spin, and they were measured from the GW15914 ring-down with enough precision to confirm that the final object was indeed a black hole of the inferred mass and spin, consistent with general relativity's prediction of the no-hair theorem. The confirmation that GW15914 was produced by two black holes, rather than by some other compact objects such as neutron stars or exotic matter configurations, rested on multiple lines of evidence. The masses inferred from the waveform were far too large to be neutron stars, which have a maximum mass of roughly 2 to 3 solar masses. The final object, at 62 solar masses, was far too massive and compact to be any known type of object other than a black hole. The ring-down frequency was consistent with the quasi-normal mode frequency of a black hole of the inferred mass, and the merger dynamics, in which the two objects approached to within kilometers of each other at near relativistic velocities without any tidal disruption or electromagnetic emission that would be expected from neutron stars or other matter-filled objects, were consistent only with the merger of two black holes whose interiors are entirely within their event horizons and can produce no electromagnetic radiation. GW15914 was a black hole merger, the first ever directly observed, opening a new chapter in our understanding of the most extreme gravitational objects in the universe. When the LIGO collaboration announced the detection of GW15914 in February 2016, the simultaneous announcement of what the signal represented was equally significant. The waveform matched the predictions of general relativity to extraordinary precision. This was not merely a confirmation that gravitational waves exist. It was a confirmation that general relativity, the theory that predicted gravitational waves in 1916 as a consequence of its description of gravity as the curvature of spacetime, accurately describes the behavior of two black holes each tens of times the mass of the Sun, moving at a significant fraction of the speed of light, in a fully nonlinear and dynamically extreme gravitational environment unlike anything previously tested. The agreement between observation and theory for GW15914 represented the most demanding test general relativity has ever been subjected to, and it passed. General relativity had been tested extensively before GW15914 and had passed every test that had been devised for it. The precession of Mercury's perihelion, a small discrepancy in Mercury's orbit that Newton's gravity could not explain but that fell out of Einstein's equations as an immediate consequence, was one of the first confirmations in 1915. The bending of starlight by the Sun's gravity, measured by Arthur Eddington during the solar eclipse of 1919, provided the first experimental confirmation that the theory was correct and made Einstein famous worldwide. The gravitational redshift of light climbing out of a gravitational well, the Shapiro delay of radio signals passing close to the Sun, the frame-dragging effect of Earth's rotation on spacetime measured by the Gravity Probe B satellite, all confirmed general relativity in various aspects. But all of these tests were in the weak field, slow-motion regime, where the gravitational fields are weak and the velocities are much less than the speed of light, and where the theory can be approximated by perturbative calculations. The regime probed by binary black hole mergers is qualitatively different. When two black holes, each of 30 or more solar masses, orbit each other with a separation of only a few hundred kilometers, with orbital velocities approaching the speed of light, the gravitational fields are of order unity in dimensionless units, meaning they are not small perturbations on flat spacetime, but order 1 distortions of the spacetime geometry. The standard perturbative approximations that work in weak field tests break down entirely, and the behavior of the system must be calculated by numerically integrating Einstein's field equations directly on a computational grid. This is an enormous calculation. Einstein's equations in full generality are a set of 10 coupled, nonlinear partial differential equations in 4 spacetime dimensions, and solving them numerically for the merger of two black holes with sufficient accuracy to compare against gravitational wave observations required decades of development in numerical relativity and the use of some of the most powerful computers in the world. The fact that the numerical relativity templates match GW1-50914 is thus a test of general relativity in a regime that is as far from weak field gravity as it is possible to go while still being accessible to observation. It tests not just the linearized approximation to general relativity that was used to predict gravitational wave emission in 1916, but the full nonlinear Einstein equations in the most dynamical and strongly curved spacetime geometries that can be observed. The agreement is at the level of a few percent, constrained by the signal-to-noise ratio of the detection, and within these limits, there is no evidence of any deviation from general relativity. The tests of general relativity performed on GW1-50914 and subsequent events take several specific forms. One approach tests whether the inspiral waveform matches post-Newtonian predictions at each order of approximation. Post-Newtonian theory expands the gravitational wave emission in powers of the orbital velocity divided by the speed of light, generating a series of correction terms that become important as the velocity increases. If general relativity is the correct theory, the coefficients of each of these correction terms should take specific values determined by the theory, allowing these coefficients to vary freely and fitting them to the observed waveform tests whether the data require any deviation from the predicted values. For GW1-50914 and subsequent events, no significant deviation from the general relativity predictions has been found. A second approach tests the consistency of the inspiral and ring-down phases. The inspiral phase determines the masses and spins of the two initial black holes. The ring-down phase determines the mass and spin of the final black hole. General relativity predicts a specific relationship between the initial and final masses and spins through the binary black hole merger dynamics, and this relationship can be tested by checking whether the inspiral and ring-down parameters are mutually consistent. For GW1-50914, the final black hole mass and spin inferred from the ring-down are consistent with the values predicted from the initial parameters inferred from the inspiral, with the energy and angular momentum balance expected from numerical relativity. This test, called the inspiral merger ring-down consistency test, is passed with the data from GW1-50914 and from the growing catalog of subsequent events. The broader significance of general relativity's confirmation in the strong field dynamical regime is that it closes a long-standing gap in our experimental knowledge of gravity. We know that general relativity is correct in the weak field regime from solar system tests, in the moderately strong static field regime from neutron star and black hole X-ray binary observations, and in the strong field dynamical regime from binary pulsar observations. But the binary pulsar tests are indirect. They confirm that energy is lost at the rate general relativity predicts, without directly observing the gravitational waves. LIGO's detections provided the first direct observation of the strong field dynamical behavior, and the agreement with predictions is the strongest confirmation yet that Einstein's vision of gravity as the geometry of curved spacetime is not merely approximately correct in some regimes, but fundamentally correct in the most extreme gravitational environments the universe provides. Every form of electromagnetic radiation known to astronomy is stopped, scattered, absorbed, or distorted by matter in its path. Radio waves pass through gas clouds but are reflected by ionospheres and absorbed by water. Infrared light is absorbed by interstellar dust. Visible light is scattered by gas and blocked by dense clouds. Ultraviolet radiation is absorbed by ozone and by molecular hydrogen. X-rays are attenuated by gas columns. Gamma rays are converted to electron-positron pairs by intense magnetic fields and absorbed by intervening radiation fields. The universe is, in different degrees and at different wavelengths, opaque to electromagnetic radiation. This opacity is not merely an inconvenience for astronomers. It is a fundamental limitation on what can be seen. Entire regions of the universe, the interiors of molecular clouds, the cores of galaxy mergers, the dense accretion disks around supermassive black holes, and above all the interior of the Big Bang itself, are permanently hidden from electromagnetic astronomy by the material that surrounds them. Gravitational waves are not subject to any of these limitations. They are not absorbed by interstellar dust because dust interacts with gravitational waves through tidal forces that are entirely negligible at astrophysical densities. The coupling between a gravitational wave and a collection of ordinary matter is so weak that even a galaxy-wide column of stellar material would attenuate a gravitational wave by an amount that is unmeasurably small. They are not scattered by electrons or protons because the gravitational wave matter cross-section is incomparably smaller than any electromagnetic cross-section. They are not blocked by magnetic fields because magnetic fields are electromagnetic phenomena that couple to charged particles, and gravitational waves interact only through the curvature they produce in spacetime. The universe is, to a remarkable degree of approximation, completely transparent to gravitational waves. This transparency is a direct consequence of the weakness of gravity as a force. Of the four fundamental forces, gravity is by far the weakest. The gravitational attraction between an electron and a proton is weaker than their electromagnetic attraction by a factor of about 10 to the power of 39. This extraordinary weakness means that a gravitational wave, which perturbs the gravitational field and therefore interacts with matter through gravity, interacts with any given piece of matter only extremely weakly. The cross-section for a gravitational wave to be absorbed by an atom is so small that even a density of matter equal to the average density of the universe, accumulated over the entire observable radius of the universe, would absorb a negligible fraction of the wave's energy. For all practical observational purposes, gravitational waves propagate through the universe without any attenuation by matter. The practical implications for astronomy are profound. A gravitational wave source can be observed regardless of what lies between it and the detector. A binary black hole merger in the center of a dense molecular cloud, hidden from all electromagnetic observation by the dust and gas surrounding it, is as visible in gravitational waves as if it were in empty space. A neutron star merger deep in the core of a galaxy, where the density of stars, gas, and dust makes the immediate environment completely opaque electromagnetically, sends its gravitational wave signal outward through all of this material without the slightest attenuation. The gravitational wave sky is a sky without fog, without dust lanes, without the zones of avoidance that afflict optical and radio surveys of the galaxy. Every compact object merger in the universe, regardless of its electromagnetic environment, is potentially detectable if its distance is within the range of the gravitational wave detector. The only factor that limits the detectability of a gravitational wave source is its intrinsic amplitude and distance. Gravitational wave strain falls as 1 over distance, so that a source 3 times farther away produces a signal 1/3 the amplitude. The noise floor of the detector sets a minimum detectable strain, and this determines the maximum distance, called the horizon distance, at which a source of given intrinsic amplitude can be detected. For current LIGO sensitivity, the horizon distance for stellar mass binary black hole mergers of the GW159 warm tour type is a few billion light-years, encompassing a volume containing billions of galaxies and an enormous number of potential merger events. This horizon will expand as detector sensitivity improves, eventually reaching a significant fraction of the observable universe for the most massive mergers. The transparency of the universe to gravitational waves also means that gravitational Wave astronomy can, in principle, probe cosmic history to earlier times than electromagnetic astronomy. The cosmic microwave background reaches back to 380,000 years after the Big Bang. Gravitational waves from phase transitions in the early universe, from cosmic string networks formed shortly after the Big Bang, or from the inflationary epoch itself, would arrive at detectors today essentially unaffected by their journey through all the matter and radiation that have existed since they were generated. The detection of any of these primordial gravitational waves would be a window onto the universe at energies and times completely inaccessible to any electromagnetic or neutrino observation, providing direct observational evidence about the very earliest moments of cosmic history. The contrast between the richness of information available to gravitational wave astronomy and the limitations of electromagnetic astronomy is not a comparison of better versus worse techniques, but of complementary tools sensitive to different aspects of physical reality. The electromagnetic universe, made visible by the interaction of light with matter, reveals the distribution of ordinary matter, the temperature and composition of gas, the energy output of nuclear reactions, and the dynamics of charged particles in magnetic fields. The gravitational wave universe, made visible by the interaction of spacetime distortions with inertial masses, reveals the distribution of all mass and energy regardless of its charge or temperature, the dynamics of the most compact and gravitationally extreme objects, and potentially the structure of spacetime itself in regimes of extreme curvature. Together, the electromagnetic and gravitational wave skies provide a complete picture that neither can provide alone, and the universe that emerges from combining both is richer, stranger, and more informative than either view individually. In the catalog of gravitational wave detections, GW170817 occupies a unique place. It was not the first detection, not the strongest signal, not the source of the most massive black hole merger. What it was, on August 17, 2017, was the most scientifically productive single astronomical event ever observed, a moment when the convergence of gravitational wave and electromagnetic observations of the same event opened a new era in astronomy and confirmed, in a single observation, theories that physicists and astrophysicists had spent decades developing. The event was the merger of two neutron stars in the galaxy NGC 4993, approximately 130 million light-years away, and the cascade of scientific results that followed from its detection transformed our understanding of neutron star physics, heavy element nucleosynthesis, the speed of gravity, the expansion of the universe, and the astrophysics of gamma-ray bursts. The gravitational wave signal from GD170817 was fundamentally different from the binary black hole mergers that had preceded it, where black hole mergers produce a short, sharp chirp lasting less than a second for the most massive systems. The neutron-star merger of GW170817 produced a gravitational wave signal lasting approximately 100 seconds, sweeping upward in frequency from 24 Hz to the merger frequency as the two neutron stars, each about 1.4 times the mass of the Sun, spiraled together from a separation of hundreds of kilometers down to contact. The longer duration of the signal, compared to black hole mergers, resulted from the lower masses of the merging objects. Less massive and spiraling bodies lose energy more slowly and therefore take longer to complete the merger. Over the 100 seconds of the signal, LIGO and Virgo accumulated information about the neutron stars' masses, their spins, and, uniquely, their tidal deformability. Tidal deformability is a property that distinguishes neutron stars from black holes. In a fundamental way, a neutron star has a finite size and can be deformed by the tidal gravitational field of its companion, while a black hole in general relativity has zero tidal deformability. As the neutron stars in GW170817 approached each other, the tidal forces each exerted on the other distorted their shapes, and these distortions affected the gravitational wave emission in a way that depends on the stiffness of neutron star matter. How stiffly neutron star matter resists compression, which is described by the equation of state of dense nuclear matter, determines how large and how deformable a neutron star of a given mass is. Measuring the tidal deformability from the GW170817 waveform provided the first direct observational constraint on the equation of state of ultra-dense nuclear matter under conditions that cannot be reproduced in any terrestrial laboratory. Exactly. 1.7 seconds after the gravitational wave signal from the merger arrived at LIGO and Virgo, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same direction in the sky. This detection, and the near simultaneity of the gravitational wave and gamma-ray arrivals after a 130 million light-year journey, confirmed in a single observation three things that had been predicted but never directly verified. That's short. Gamma-ray bursts are produced by neutron star mergers, that gravitational waves and gamma rays travel at the same speed, and that the delay between merger and gamma-ray burst is of order 1 to 2 seconds, consistent with the time needed for a relativistic jet to form and punch through the merger debris. The long-standing question of the origin of short gamma-ray bursts, among the most energetic explosions in the universe, was answered definitively. The atoms of which you are made were created in the stars. This statement, familiar to anyone who has encountered popular astronomy writing, carries a specific and detailed truth about the nuclear processes by which the elements were synthesized from the hydrogen and helium that emerged from the Big Bang. The lightest elements, up to carbon, nitrogen, oxygen, and neon, were produced in the cores of main sequence and red giant stars by hydrogen burning, helium burning, and the successive burning of heavier elements. Elements from silicon up to iron, the most tightly bound nucleus, were produced in the cores of massive stars during their terminal evolution and were scattered into space in supernova explosions. This much has been understood since the landmark 1957 paper by Burbage, Fowler, and Hoyle, which laid out the theory of stellar nucleosynthesis and earned its authors the Crafoord Prize, with Fowler later receiving the Nobel Prize. But the heaviest elements, those beyond iron in the periodic table, present a fundamental problem for stellar nucleosynthesis. Beyond iron, fusion reactions consume more energy than they produce, so no stellar fusion process can be responsible for synthesizing them. These elements must be built by a different mechanism, neutron capture. An existing nucleus can grow heavier by absorbing a neutron, becoming an isotope with one more neutron than before. If the resulting isotope is stable, the process can continue with another neutron capture. If the resulting isotope is unstable, it can undergo beta decay, converting a neutron to a proton and emitting an electron and antineutrino, producing a nucleus with one more proton and therefore a different element. By a sequence of neutron captures and beta decays, nuclei can be built up along the chart of Nuclides to produce heavier and heavier elements. The rate of neutron capture relative to beta decay determines which elements are synthesized. In a slow process, called the S process, beta decay is fast compared to neutron capture, so the nucleus beta decays to stability between each capture. The S process, which occurs in the outer envelopes of evolved red giant stars, builds up elements along the valley of stability in the chart of nuclides, producing elements from strontium to lead along a specific pathway through nuclear structure, space. The S process cannot produce the heaviest elements, however, because it cannot produce the neutron-rich nuclei needed to reach the actinides and the trans-lead elements. For these, a rapid process is required. In the rapid neutron capture process, the ER process, neutron captures are much faster than beta decays. A seed nucleus captures neutrons one after another without time to beta decay, building up into extremely neutron-rich isotopes far from the valley of stability. Only when the neutron supply is exhausted does the nucleus cascade back toward stability through a sequence of beta decays, arriving at a stable nucleus that may be significantly heavier than the seed. The R process requires an extraordinary neutron flux. The neutron density must be of order 10 to the power of 22 neutrons per cubic centimeter or more, conditions that can be achieved only in the most extreme astrophysical environments. This requirement makes the site of R process nucleosynthesis one of the fundamental questions of nuclear astrophysics. Where in the universe does matter with such extreme neutron density actually exist? For decades, core collapse supernovae were the leading candidate. The inner core of a collapsing massive star reaches neutron star densities briefly during the bounce, and the neutrino-driven wind that blows off the nascent neutron star's surface in the seconds following the bounce was theorized to be a site of neutron-rich conditions suitable for R process nucleosynthesis. But detailed calculations of neutrino-driven winds and supernova models consistently failed to achieve the required conditions. The entropy and neutron-to-proton ratio in the wind were not sufficient to produce the heavy R process elements. Theorists proposed various modifications to the supernova mechanism, including magnetorotational jets from rapidly rotating, strongly magnetized progenitors as alternative supernova R process sites, but none could be conclusively confirmed by observations.